So up until this point, the probably the most prominent thing in all the practice we've been doing is derivatives, limits, and quadratics. So in this video, I'm going to attempt to explain what integrals are and what the fundamental theorem of calculus is, trying to connect all of those things. Okay, so right now I just graphed y equals x squared, a function that we should be used to seeing by now. And so far we can do lots of things. We can find the vertex of this. We can find the instantaneous slope of this thing. So if I wanted to find the slope at, say, x equaled 0.6, I could differentiate this function, right? So the dy by dx with respect to x, right, would be 2x. So for any x, the slope of this will just be 2 times x. So at 0.6, it'll be 2 times 0.6, which will give me 1.2. So the slope of this at the point 0.6 will be 1.2 units. Okay, so that's what derivatives are. And like I said, we can find the vertex, the slope, all sorts of things. We could find how far it's shifted, how far it's stretched horizontally and vertically. But integration is what's called an inverse operation to differentiation. So we know how to find the slope of this, but what if we wanted to find the area underneath this curve? So one way to estimate it is, let's say we wanted to find the area from the curve, or under the curve from the point 0.4, so right here, to let's say 0.8. So what we could do is, we could draw a bunch of rectangles. So let's draw a rectangle from here to here. Color it in. We could draw another rectangle from here to here. So every zero point 0.1 units, or I guess every 2 units, every 0.1 kind of numbers, we're going to go from 0.4 to 0.5, 0.5 to 0.6, 0.6 to 0.7, and we're going to add a bunch of these tiny rectangles, and we can count those areas up because we know how to find the area of a rectangle, and we're going to get, a decent estimate of what the area under this shape is from in a certain interval a to b. In this case, it's 0.4 to 0.8. Another way to do it, so this is called a left Riemann sum. So we're going from the left side of our starting point and we're going to the right, straight across and straight down. New point, straight across, straight down. New point, straight across, straight down. And we could calculate the area of each rectangle and sum them all up. That's why it's called a Riemann sum, and we're going to get an estimate for the area under this curve. We can do the same thing, except we can start on the right side. So if we're going from 0.4 to 0.8, right, we could start at 0.5 at the top here on the right side, go down, or go over and down. Same thing here, go over, down, go over, down, over, down. And we can just keep summing up all of these areas, but you'll notice that for this one, in the last one we were underestimating this, in this one we're overestimating it because the area underneath the curve doesn't include this little part here, this area, or this area, or this area. So every time we go over, we're overestimating the area of this curve. Another way we could do it is called a midpoint Riemann sum. So what we just said was a right Riemann sum. This is a midpoint Riemann sum, is we start somewhere in the middle, in between 0.4 and 0.5, we go across. And then we go in between 0.5 and 0.6. So right here, we go across and down. And this is a bit better of a guess because we're overestimating here, we're underestimating here, and hopefully those will cancel out a decent amount, right? Because this area and this area, they seem to be pretty similar. So for something like y equals x squared, those over and underestimations hopefully cancel out. Okay, so that's called a midpoint Riemann sum. Those are kind of some strategies to help estimate. Another way you could do it is, well, you could say, since this curve is kind of going up like this, it's not a straight line like rectangles, what if we did a trapezoid estimation? And you can totally do that. So the formula for a trapezoid like this, for example, if we went from here to, whoa, what's that? Went from here to here and then straight down, that's a bit of a better estimate, right? from here to here, and then straight down, and this function is going to get steeper and steeper and steeper, right? So the trapezoid shape's going to change, but we can start from this height of the function to this height, and we can just kind of draw a line straight down and keep summing up the area of these trapezoids. So the formula for this would be, let's say that we'll call this the height 1 and height 2 of the trapezoid. It'll be the two heights added up divided by 2. So this will just be the average height between height 1 and height 2, and we're going to multiply it by the width, right? So this is basically like the same as the area of a triangle between like having a height in between the two and the same width. That's really what this formula is doing. And you could sum all those up, and that would also be a decent guess for the area under this curve. Now, if we want to get more and more accurate, what things do we have to do? Because right now what we're doing is we're summing up a bunch of rectangles which aren't exactly the same as the actual units or things kind of being encapsulated underneath the curve. And same with trapezoids. So this curve isn't a straight line, right? It's curved. And everything that we've been doing to sum up the areas is straight. It doesn't have curves. It's rectangles that are straight, and it's trapezoids which are straight. And for different shapes, neither of these are going to work perfectly unless it's a linear function. So unless it's like y equals x like this, we could just use our knowledge of geometry. But what's a way that we could figure out a function to describe the area underneath any given curve that's continuous along some interval? Well, we could think of it in terms of limits. Okay, so one thing that we have to do is we have to add up more rectangles to get more accurate. So what if we, instead of doing 2 squares, we just did 1? Whoops. What if we just did 1? So as opposed to doing 2, what if we just did 1 here? Right? That would give us a better estimate. So what we're doing when we decrease this space is we're decreasing this distance here. So we're decreasing change in x. And we're also increasing, we're increasing the number of rectangles we have. So the area underneath this curve, I'll just write it A. This is equal to what's called the integral. So let's say we're going from, just to make it easy, from 0. Let's say we're going from 0 over here to 1. We're going from 0 to 1. So from there and there. We're trying to figure out the area underneath the curve from 0 to 1. How can we do that? So we're going to call it A. We're trying to find some function that's going to represent this area. And the way we write it is through what's called a definite integral. So it's like an elongated S, which kind of I think of as sum. So this S, this integral, stands for us summing up all the rectangles as change in x, right, from this point to this point, becomes infinitely small. So we're summing up all the rectangles with widths that are infinitely small and an infinite number of infinitely skinny rectangles. So the area is equal to the definite integral, it's called, from 0 to our point 1, of our function f of x, which is also equal to x squared, and then dx. So anytime we have an integral, we have our integral symbol, which is this elongated s, and if it's a definite integral like this one is, we're taking our two upper and lower bounds. So our lower bound is 0 because that's our lower number, it's most to the left on the graph, and our upper bound is 1 because that's most to the right. So the smaller number always goes on the bottom. F of x is our function, and dx is just basically the change in x. So what this is really saying is the formula for a rectangle, right? The area of a rectangle is the length times the width. So what we're saying is we're going to sum, that's what this S is, this integral, we're summing all of the areas of the length of the function. So basically the function's height, which is f of x. So let's say at 0.6, this was the length, this was the height of the function, times its change in x, which is that dx. So times dx, where dx is the difference, the change, the delta in x. And you can see that's going to give us a rectangle here that's not perfect, but when the change in x and the number of rectangles is infinitely large, and the change in x is infinitely small, we're going to get the exact area under the curve. So that's how you'd write it out. That's how you write out an integral, a definite integral in this case. And that is also going to be equal to, as a limit, right? Because we're talking a lot about infinitely large and small things. The limit as the change in x approaches 0 of the sum, because we're summing all of these things up, right? We're starting with one rectangle and we're going all the way to an infinite number of rectangles of f, you can call it I of x. So for some given function height, fi of x times the change in x. So that's how you do the notation. This basically means we have an infinite number of rectangles, right? That's what this infinity means on top of the sigma. And delta x is approaching 0. So we're saying we have an infinite number of rectangles, but the rectangles are also infinitely small. And if we sum all of them up using calculus, that's going to give us some function that can relate the actual function itself to the function of the area underneath the function. Okay? So that's the main idea here. So writing it more generally, instead of 0 and 1, I'll just write a for some constant and x for some upper bound. So let's say our a was 0 and x is a variable. So the function, the integral of f of x, is going to be dependent on where x is. So it can kind of move to the left or the right. We can choose a spot and we can calculate the area underneath the curve by using the integral symbol there. Okay, so what is the integral of something like x squared? Well, like I said before, integrals are the inverse of derivatives. So if we had f of x equals x squared, we know that f prime of x equals 2x because we reduced the exponent by 1, so I'll write 2x to the power 1. We reduced the exponent by 1 and we brought this 2 out to the front. Well, how would we go the opposite way? What if we took the integral of f prime of x? And I'm simplifying it. I'll get to the details right now, but this is just kind of the main idea. If we take the integral of the derivative, we just get the same thing back. We get x squared. And there's going to be a plus c, which I'll talk about in a sec. But just for simplicity reasons, if we take the integral of a derivative, we just get the initial function back because they're inverse operations. So let's say we didn't know what the original function was. Let's say we knew the derivative was, for example, let's say the derivative, I'll write g prime of x was equal to, let's go 3x. Okay, how could we find g of x? Right, well, in theory, we would just do the opposite of the power rule for differentiation to this 3x. So instead of bringing the 2 out front, like we did in x squared, or bringing the exponent out, multiplying it to the coefficient, and lowering the exponent by 1, what we're going to do is we're going to increase the exponent by 1, so it'll be 3x squared, and we're going to divide by that new exponent instead of multiplying. So this is going to be 3 halves x squared, right? Because we're just kind of doing the opposite of the power rule for differentiation. So that's the main idea behind integration. Obviously, it can get harder, and there's tricks that you can use that I'll talk about in my videos. I'm going to talk about a lot about integration, okay? So no need to worry about that, but this is just kind of like the introduction to what it actually is intuitively. So we're taking the integral from a to x of f of x dx. This dx just means what variable are we taking the derivative with respect to. And I actually wrote this wrong here. Because the bounds have x in them, like this, we can't write f of x dx. We have to write what's called the dummy variable. So lots of the time they use t. So f of t dt. We're calling this original function f of t. Because if we have x in our bound, in our upper bound, that's what's making the function a function and dependent on a variable. If we have f of x dx and then we integrate it with respect to x, with x in our bound, we're going to get like x's everywhere and it's not going to look pretty, okay? So when we're taking the derivative with a variable in our bounds, we have to use a dummy variable for our actual function. Okay, that's also important. So that's the main idea. So what is the fundamental theorem of calculus? Okay, so I'm talking a lot about like how to estimate areas underneath a curve. I'm talking about limits as n approaches infinity, delta x approaches 0. But what is the actual fundamental theorem of calculus? Well, let's say we want some function f of x, capital F of x, to represent our area underneath the curve. So capital F of x, that's often how it's denoted. And I kind of went into it a bit before. That's going to be the integral from some constant a to our variable x. So the function is dependent on x of our variable, or our function, sorry, not f of x, f of t, our dummy variable dt, right? That's going to be the integral. And let's say we wanted to take the derivative of this function, capital F of x. So let's say we wanted df, d capital F by dt, instead of d lowercase f. Well, since we know f is the integral from a to x of f of t dt, this is just going to be d by dx. And instead of dt, I'm going to write dx just to make it a bit easier. This is going to be the derivative with respect to x of the integral from a to x of f of t dt. So we know f of x is this integral here, and the derivative of that is just going to be the inverse operation. We're applying this operator onto this integral. And what this is going to equal is f of x every single time. So if you have some crazy function, right? If you have some crazy function like sine squareds and natural logs and stuff, and that is what you're integrating and then differentiating, all that you're going to need to do is replace the t's in your function with x's. So let's say you were taking the derivative with respect to x from, let's go a to x, right? Or we don't even need to do a, we can write an actual number. Let's do pi. From pi to x of, I don't know, sine squared t ln, or we can do like plus the natural log of x minus 1 or something crazy like that. Okay, and we're differentiating, not x, but t. I keep mixing up my variables here. T minus 1 dt. This is just going to be the function itself, except every single time we see t, we're replacing it with x. So this will be sine squared of x plus ln x minus 1. Okay, and we're going to need nothing after that, because this pi here, if we differentiate the function where we replace t with pi, that's going to give us a constant, and if we differentiate that, that's going to give us 0. So we're just going to go minus 0, and we never need to worry about this lower bound if it's a constant. Okay, so the second part of the fundamental theorem of calculus says if we're looking for some function capital F of x, which is the derivative or the integral from a to x of f of t dt, I keep writing x, I'm going to punch the screen, just a habit here, f of t dt, this is going to be equal to capital F, or instead of x, I'm going to write b. So let's say we want the exact area, for example, from 0 to 1. So let's say we were explicitly going from 0 to 1, and we wanted the area underneath this curve exactly. So we would use a definite integral using the fundamental theorem of calculus. This would be the function capital F of b minus the capital F of a. So what we're doing is we're evaluating this integral, substituting in b where we see t, and then we're going to subtract the integral of this function, substituting a where we see t. And that is going to give us the exact area under the curve between the points 0 and 1, or generally a and b. Okay, so that's the main idea behind the fundamental theorem of calculus. I'm going to be talking a lot about tricks for integrating, how we can do complex integration. Like there's lots of qualities and different um, different properties of integrals that we can apply that are super helpful. I'll be talking about those different techniques. Maybe two things are multiplying or dividing. We're not sure what to do, right? Because it's not always going to be as simple as y equals x squared, right? Because for this one, we can just use the power rule if we want to integrate, right? X squared dx from maybe 1 to 5. This is called a definite integral. All we need to do for this is raise the exponent by 1 and divide by that new exponent. So x to the third over 3. And we need this plus c, but I'm not going to talk about that right now. And what we do is we substitute in 5 for x, and then we substitute in 1 for x, and we take the difference between those. So this will be 5 cubed over 3 minus 1 cubed over 3. And this is going to give you the area under the curve. I don't have my calculator here, but it'll be 125 over 3, whatever that is, minus a third. So it's going to be 125 over 3 minus a third. So it'll be 124 over 3. I'm sure that's actually going to be, you can't divide that by 3, so you leave it as a fraction, but that's going to be about 40. Okay, so 40 units is going to be your area. That's kind of the main idea, but it's not always going to be as simple as my point as just x squared dx. It's going to get pretty hard, and don't worry, if you follow along the videos, you'll learn lots of tools to be able to solve these problems. So I'll see you in my next video where we talk about properties of integrals, and yeah.